Hello there. So, if I miss one day, no big deal. If I miss 2 days, I'm going to send you a video. Here we go. Let's talk a little bit about the, that thing we do. I got nothing. Okay. Let's do some math. Okay, here we go. So, up here, I'm just so not ready for this, but hey, welcome to class. A general discussion of sections 3.3 and 3.4 on first and second derivatives. So, I made this graph. I didn't make this graph. Desmos made this graph, but I put in the functions. And here in green, we have our original function. And our original function is always going to tell you the roots or the zeros of the function, right? It tells you all the y values in any point we want to put in as important information. All the y values will come from the original. The original function tells us the domain. It gives us ideas about continuity. From the original function, we find the first derivative, right? Graphed here in red. The first derivative tells us where our critical numbers are. Critical numbers are when the first derivative is 0 or the first derivative does not exist. It tells us the intervals or the x values where the original function is increasing or decreasing. It tells us the differentiability, right? Are we able to find the derivative? Where does the derivative exist? And it tells us the locations of our maximums and minimums. And then in black, I have our second derivative graphed. And the second derivative will tell us points of inflection. This is where the second derivative is equal to 0. It's like a hinge point. Think of it like this. Let me grab my marker here real quick. This is concave down, and then the graph turns into concave up. This right here is our point of inflection. It's where it changes from concave down to now we're looking at concave up, or vice versa. It could go concave up to concave down, right? Just a hinge point. It tells us the intervals of concavity. It'll tell us all of the x values where the function is concave down. It'll tell us all the x values where the function is concave up. But it'll also help us with the maximum and minimum locations, so we can find those using first or second derivative. The most important thing to do is keep in mind that the derivatives tell us where to look. It only gives us information about the x values. The original function is always going to tell us what the value actually is, the actual y value. So your work with the second derivative and concavity is much the same as your work with the first derivative and intervals of increasing and decreasing. So let's look at some examples. I said some here, but with my energy level today, at some means 2. All right, example 1. Excuse me, that's what happens when I take a sick day. I'm sick. Okay. Consider the function below. F of x equals negative 2x squared plus 4x plus 1. This isn't a terribly exciting example, but it has everything going on together, and we don't always have to work hard. Sometimes we could just do work. If I want to find the critical numbers of f, this tells me I want to set the first derivative equal to 0. Because it's a polynomial, there will never be a place where the derivative does not exist. Polynomials are continuous and infinitely different. They're not infinitely differentiable. They're as differentiable as you can until you get constants, and then the rest of the derivatives will be 0. But we can always find the derivative of a polynomial. All right, so let's find the critical numbers. So first thing I do is I take my derivative, f prime of x, equals negative 4x plus 4. I'm going to set it equal to 0. And when I solve correctly, I'll get x equals 1. Alright, so this is our only critical number. X equals 1, something important happens. So let's see what that something is. Remember, the derivative is going to be in black, and I'm going to use other colors for other important values here. X equals 1, here's 1. Now what I'm going to do is I'm going to use a test value, any value to the left, and it just occurred to me that I think I did this exact same problem in class. I'm going to do it again anyway. Any number to the left, let's take 0. Any number to the right of 1, let's take 2. And what we know is this. Because of this critical number, something important happens here at 1. So from negative infinity to 1, it's all going to be the same. And from 1 to infinity, all that stuff is going to be in the same. Whatever this critical number of 1 tells us, it's going to uniformly, not uniformly, I can't even think today. 1 is going to cut our number line into 2 intervals, and we're going to find out how those intervals are described. So I'm going to test. I'm looking for a sign only, S-I-G-N, so plus or minus. So the derivative at 0 is negative 4 times 0 plus 4, which is positive. So I know here my derivative is positive, and if my derivative is positive, I know my function is increasing. I'm going to take my derivative at 2, negative 4 times 2 plus 4 is negative 8 plus 4, and I do not care that it's negative 4, I only care that it's negative. Because if the derivative is negative, the function will be decreasing here. And I know this, and it's automatic, even though I forgot to read part B, what's going to happen. So let's go back and fill in our answer here in part A. Our critical number is x equals 1. The point is 1, comma, go back to the original f of 1. Okay, the original function f of 1. Part B, I automatically did this with my number line and test values. Number line and test values. Anytime I'm asked to find a critical number and then there's stuff that comes after it, I automatically go to my number line, my sign chart, and see where the derivative is positive, where the derivative is negative, because if there's more than just the critical number we're looking for, that's probably what it's going to be. So our number line and test values tell me my derivative is positive here on the interval from negative infinity to 1, so the graph is increasing from negative infinity to 1. My derivative is negative on the right of x equals 1, so for 2 and any value higher, actually for 1.000000001 and higher, our derivative is going to be negative, so that's going to be our interval of decrease. Alright, now the first derivative test to identify the relative extrema, that's what we did here. By finding the first derivative is positive and then negative, the first derivative test tells us if it changes positive to negative at a critical number, the critical number is a maximum. It's a location of a maximum. Location is far too many letters. If it changes negative to positive at a critical number, the critical number is the location of a minimum. And here we can see that we have a maximum at 1. So the relative maximum, remember the y value always comes from the original function. I should have just found it back here. I didn't. So let's find it now. F of 1 equals negative 2 times 1 squared plus, let's see what this function was, 4 times 1 plus 1. 1 squared is 1. Negative 2 times 1 is negative 2 plus 4 plus 1. Here we see that this is actually a vertex for the function. Negative 2 plus 4 is 2. 2 plus 1 is 3. So my relative maximum is at the point 1 comma 3. Remember, it already has the parentheses for you, but don't get lazy. Keep in mind, you got to put the parentheses around a point. This is a quadratic. This is a quadratic function that opens down. We know this from pre-calculus. And it only has a maximum. It does not have a minimum. So in this case, the minimum does not exist. All right. Find the derivative, set it equal to 0, sign chart. Based on positives or negatives, we find out what's going on with our function. So let's do it again. Only this time it says something slightly different, and I've made it harder by including trig. Find the point of inflection of the graph. The point of inflection is always, first of all, I call it POI. If you've ever been to Hawaii and eaten poi, and you didn't grow up on it, it's nasty. So every time I talk about points of inflection, I think of Hawaii. The overall good thoughts of Hawaii, just not poi, never again. Points of inflection tell us that the second derivative is 0, or does not exist. But again, actually no, the second derivative does not exist. That's not going to be a point of inflection because it's not a point on the graph, probably, or it's a weird thing. We're going to pretend I didn't say that for the last 20 seconds, okay? Point of inflection, we're going to set the second derivative equal to 0. That's it. So let's do that. Let's remind ourselves over here of our little derivative circle. Our derivative circle goes around clockwise. So if I want to take my original function, x plus 7 cosine of x, and I'm going to keep an eye on this interval. First I take the first derivative, 1 plus 7 times minus sine x, which for most of you would have been 1 minus 7 sine of x. Then I'm going to take the second derivative. The only way to find the second derivative is to take the derivative of the first derivative. So the derivative of 1 is 0, minus 7. The derivative of sine is cosine. So this is minus 7 cosine of x. Okay. So in this case, right, my second derivative, now I want to find where's my second derivative equal to 0. So I want to solve. 0 equals minus 7 cosine of x. Let's divide both sides by negative 7. Oh, isn't that cool? 0 divided by whatever. That's 0. And we know on the interval from 0 to 2 pi, that cosine, right, cosine graph looks like a C. So we'll call this our 2 pi. So we know that cosine is 0 here at pi over 2. Sorry, big hesitation there. And 3 pi over 2. If you need to think in terms of the unit circle instead of the graph of cosine, absolutely do it. Whatever you need to do, you do. But these are our points of inflection. Kind of. These are the locations of the points of inflection. Okay, and so if they're just the locations and I want the points, now what I have to do is go back to the original and I find f of pi over 2. That's going to be pi over 2 plus 7 cosine of pi over 2. But we know that cosine of pi over 2 is 0. It says so right here. So 7 times 0 is 0. And this turns out just to be the x value. So pi over 2, comma pi over 2. And some of you already know the answer to this next one. due to the symmetry of it all, if I put in 3 pi over 2, the cosine of 3 pi over 2 is also 0. 7 times 0 is 0, and we're going to get 3 pi over 2. Do not expect this to happen every time. I just happened to pick that one example that it works out like this, but you do have to evaluate to make this happen, to find your y values. Okay, it doesn't always happen like that. Now I want to describe my concavity. So keep in mind that my interval here starts at 0 and ends at 2 pi. Because I'm told so right here. So I don't care about anything negative. I don't care about anything bigger than 2 pi. I only care about, let's make that a pi, the interval from 0 to 2 pi. And I have my points of inflection. So I'm going to put pi over 2 and 3 pi over 2 as my markers here on my number line. And then I'm going to find some test values. So I'll use pi over 4. In between, I'll use pi. And over here, let's go with 7 pi over 4. I like the pi over 4s because I remember those a lot easier than pi over 6 and pi over 3. I have to like slow down for a couple of seconds there. But with the pi over 4s, it's easier for me to remember. Keep in mind, we're looking at these intervals. All right, for intervals of concavity, these are our only options. Make sure your intervals stop. They'll start at 0, end at 2 pi, and they're cut by our points of inflection. So if you write these down first, and then we find the sine, all right, look for the sines. The second derivative at pi over 4 is minus 7 times the cosine of pi over 4. Well, I know the cosine of pi over 4 is positive. So minus 7 times a positive number is negative. Yeah, cosine of pi over 4 is square root of 2 over 2. Square root of 2 over 2 times negative 7 is negative 7 square root of 2 over 2. But I don't care what the number is. I only care about the sign. It's negative. So a negative is down, right? Negative people frown. It goes down. It works for me. So we're concave down in that first interval. If I make a test value of pi, we'll have negative 7 times the cosine of pi. Cosine of pi, that's down here, right? Cosine of pi is negative 1. So I'll have negative 7 times a negative 1, which is positive 7. Again, don't care about the 7. I just care about the positive. Positive people generally smile. Smile goes up, it's concave up. It works for me. Try again. F prime at 7 pi over 4 is negative 7 times the cosine of 7 pi over 4. Keep in mind that's here, right? Somewhere in between here. Cosine's positive. It happens to be positive square root of 2 over 2. Again, I don't care what the number is. I just care what the sign is. And so with this, I see that this is down. This interval is concave up. And this interval is concave down. Much like we did with increasing and decreasing. So concave upward, remember it's an interval, so I'm going to put in my parentheses. They don't put these in for you because you have to decide between round and square bracket parentheses. Increasing, decreasing, concavity, always use the round ones in this book. Pi over 2, comma, 3 pi over 2, we're concave upward. From 0 to pi over 2, and again from 3 pi over 2 to 2 pi, we are concave downward. And just because I'm feeling like it. Let's take a look at, not that, a graph here. This is the one that was originally there. Let's take a look at our graph of 7 minus cosine of x. Let's take a look and make sure I put the problem in correctly. I did not. It's x plus 7 cosine of x. Wow, did I just make up a 7 in this? X plus 7 cosine of x. It would have been one of those days had I shown up, I'm just saying. And then what we want to do is, let's go ahead and restrict our axis from 0 to 2 pi. I just typed pi and it gives it to me, and I'm going to use pi over 4. So pi over 4, and yeah, we'll leave the rest of it. Y values are fine. We see here we're concave down until about pi over 2, and then the graph is concave up, and then the graph is concave down. Notice when the graph is concave up, there's a minimum value. Here's our minimum, and if we were to try to solve for the first derivative equal to 0, we could find the exact value of this minimum. I'm guessing it's going to be pretty close to 3. We don't care though. It's not, I mean, I'm not guessing. It just told me 2.99. But we could find it if we had to by setting the first derivative equal to 0, finding where sine of x is equal to 1/7. All right, that's about all the energy I have for calculus today. This is like going old school. If you've ever seen the movie Ghost, Henry VIII I am, right? First derivative, the second derivative, same as the first. It's all the same. We find the derivative, we set it equal to 0, we use our number line, we always take it back to the original for the y values, we only care about the signs. It's a sign chart actually. We only care about the signs on our, that's IGNS, on our number line here. And we can find concavity, we can find areas of increase and decrease, and I'm really hoping I'm going to be in class tomorrow. Thanks for taking the time to listen to this. I hope you're doing well. Take a mental health day whenever you need it. Take a physical health day when you need it too. I'll talk to you soon.